How do we do this? Well, we would like y equal to 0 to be at the wall. So we write y is equal to r bar. So if y is equal to 0, we want to be at the wall. So r bar minus rw to the half. Right, so what does this tell us? This tells us that if you're at the wall and r bar is equal to r omega to the half, y is 0. Whereas if r bar goes to 0, I'll go y going to minus infinity. Now I would like it to go from 0 to plus infinity, then I can just put a minus sign in front of the whole thing. Right, which really means that I'm saying r bar is equal to y minus r omega to the half. So this is my transformation, let me call it 10. And what this implies is that y equal to 0, I have h bar equal to 0. So this is the wall. Right? And this core is actually y must be equal to, for a fixed r omega, it's r omega to the half. But as r omega gets larger, right, in the limit of very, very large r omega, so we keep increasing r omega looking at the problem, it really means that as y tends to infinity, I have h being bounded. So now this is a much nicer version of the problem in this coordinate system, right, because I can now imagine that no matter how large my value of r is, sorry, let me just get this to, yes, okay. Yeah, so no matter how large my value of Rw is, I'm now going to be able to solve this problem nicely, because I can always apply the boundary condition at the wall by applying it at y equal to 0, and as y goes to infinity, I simply have to require that the solution h bar stays bounded, and I will get a solution for all values of Rw. Okay, so let's now use this transformation and substitute it into my equation 9 to get really what's called as the boundary layer equation in the near wall coordinates, which is really what a boundary layer analysis would give you. But here we've seen how both the perturbation method and scaling ideas have led us to this condition, have led us to this equation. Okay, so let's make our substitution. We get 1 over y minus rw to the half So dou by dou r bar is simply dou by dou y, right? Times again y minus rw to the half dou h bar by dou y minus I times h bar equals to minus 1. Right, so here we have, this is a new equation. Now rw to the half is a large number, so let's pull it out. So we get 1 by rw to the half into yes, just a second. Oh yes, I made a mistake in the sign. I knew something was wrong here. Right, so this is actually, yes. So if you see now, I wanted y going to plus infinity to correspond to the core, right? So what I need here, this is minus r bar, which basically means I get minus y plus r bar to the half. Yes, this makes sense. because now if y is equal to 0, r bar is r bar to the half, and as y goes to positive infinity, I get r bar starts tending to 0. It of a fixed Rw, and when y is plus Rw to the half, this becomes 0. Whereas in my earlier definition, if y was 0, I'll get r bar is equal to minus Rw to the half, which is not the correct value because the r bar coordinate is always positive. You could see it here as well. So I just made a mistake in the sign, but everything else I've written follows. So I just have to have a change in my signs here. Okay, that's fine. And now if I pull this out, I get 1 by r to the half, and I get 1 minus y Rw to the half as a factor. Dou by dou y of, again, I can pull out an Rw to the half from here. And what I get here is 1 minus y by Rw to the half. Right, yes, so this looks fine. Now you'll see these factors cancel off, which is comforting because I want this to be a leading order term. And this is my new equation for h bar in the boundary layer coordinates. Okay, so I can now seek a solution to this problem again as a perturbation series, and this time I can do it because you see, if I look for a solution as an expansion, the leading order term in which basically 1 by r omega terms would go to 0, I would get a equation that still has a second order problem in the y direction, allowing me to apply the boundary conditions that I wanted to include into the problem. Right, and because I have Rw to the half, it makes sense that I could look for a perturbation series expansion in R to the half. Right, so I look for now solving this boundary layer problem. H to the half bar plus so on. Okay, but plus high order terms, so order 1 by Rw. Okay, but again, remembering that my core solution now, where was I? Yes, the solution to the core is of order 1 by Rw. Right, so it's a leading order contribution. Moreover, this contribution came from h bar only by taking the h naught term because everything else was 0. So similarly for h bar in the near wall region, I'll also take only the leading order contribution h bar naught. Right, so I don't want to take I won't take high order terms because just forgot the bars here. Right, so I can always do that, but then it'll just give me high order corrections. Right now we'll just stick to the leading order term. So I'm just looking for the solution to h naught. So the leading order of this problem, which is just the solution to h naught, is just right, this term gets cancelled off, right, because this 1 by Rw to the half goes to 0, for the h naught problem. Similarly, this goes off. So in fact, I get dou square by dou y square h naught bar minus I times h naught is equal to minus 1. Okay. Now this equation is quite simple. Really, there's a homogeneous solution and a non-homogeneous solution, right? So the homogeneous solution basically, if I assume it to be some constant, the particular solution, if I assume it to be independent of y, right, I can see that it would just be h bar not equal to minus 1 over minus I, which is 1 over I, which is minus I. Right, so this is the particular solution. Plus, I should then look for a homogeneous solution which solves dou square by dou y square h bar naught minus I h bar naught equals 0. Right, and the solution to that generally can be obtained by looking for a form. Right, so the h bar naught let's say homogeneous, I can assume it to have the form some constant e to the power alpha y. If I substitute in here, I will see that into the equation for this, which is basically equal to 0. This is the homogeneous solution, right? I already got the particular solution here as minus I, which took care of this minus 1. So if I substitute this in here, and after some algebra, you will see I'll get a quadratic equation for alpha. Okay, and what I will find is that alpha is equal to plus minus root I. I leave that as an exercise for you. And how do you determine alpha here? Well, you must recognize that alpha is itself a complex number. So let me write alpha as a plus ib. Right, so a plus ib, this basically means a plus ib square is equal to I. And then if I solve for this, I will get a is equal to plus minus 1 by root 2. And b is also equal to plus minus 1 by root 2. Okay, so the general solution to this problem then becomes, these basically mean that I have 1 by root 2 plus I 1 by root 2 and minus 1 by root 2 minus I 1 by root 2. Both exponentiated are two possible homogeneous solutions. And I need two solutions because I have a second order homogeneous differential equation. So the solution then becomes this plus some constant b. I'll first take the positive root of alpha. Right, plus another constant times the negative root. Very nice. So this is the solution to the leading order problem that we had here from the boundary layer analysis. And now I have these two unknown coefficients that I need to determine from my boundary conditions. So remember, the boundary conditions were such that h bar must be bounded, right, as y tends to infinity, right, because I'm considering arbitrarily large values of Rw, and h bar naught must be 0 at y equal to 0. So you can see the first condition clearly implies that b must be 0, right, because exponential of y goes to infinity as y goes to infinity. So clearly b must be 0, right, and the fact that h naught must be 0 at y equal to 0 gives us what? So here I have h naught equal to 0, so I'll have I, and y going to 0 basically gives me 1, so c must be equal to I to satisfy the second boundary condition, and therefore I get the fact that h naught bar is equal to minus I into 1 plus exponential of minus y by root 2. So you see that this is a function that is 1 at the wall, but then which decays rapidly as I move away from the wall. It's sort of like what you expect for a boundary layer solution. And then this other part is really oscillatory. So I can write it as cosine y by root 2. Right, so the minus in the argument doesn't survive in the cosine, but I sine of y by root 2, the negative sign will pop out here. Okay, so this is my solution for h naught bar. And so now I can look to see what the solution is for u. So remember, u is equal to the imaginary part of e to the power I r omega t times h, which is h naught bar by r omega after our rescaling, right, to account for rescaling of velocity related h to be equal to h naught bar by rw. So I just substituted that here. Right, so because h is equal to h naught bar, which tells us really that this is an order 1 by rw effect. Okay, so now I can now write it out by again using the Euler identity for the exponential, multiplying it with the solution here, and then taking out only the imaginary components. Oh yes, before I do that, there is something important that I needed to mention. So yes, if we look at the solution for y tending to infinity, it's not just that h naught should be bounded, although here that does, already violates this case. What's also important is that as y tends to infinity, which means as I approach the core, the solution I obtain from here should match with the solution in the core. Right? Otherwise, I would have a mismatch. So that's what we see here. Yes, so the solution for h that I get, yes, for h bar naught should be equal to minus I. Right, so the h bar naught that I have there as y goes to infinity must be equal to minus I. It's not just bounded, so really it must be equal to minus I. And you see that that's indeed the case, right? So the fact that b was set to 0, both to prevent it from going unbounded, also automatically satisfies the fact that h bar naught is equal to minus I, right? So it is consistent with the solution we derived before doing the boundary layer analysis for the core. So this boundary condition it matches the core solution. So this is a typical scenario in boundary layer problems. So one of the boundary conditions is provided by the wall, right, which is to which the boundary layer is adjacent to. So that was the no slip condition, which gave us one of the coefficients, one of the unknown constants. Typically, the second unknown constant has to be obtained by what is called asymptotic matching. So we match this solution, which is valid near the wall region, to the solution of the core, which is valid only in the core. Which means that as y tends to infinity, we expect the analytical form of this solution to approach that of the solution in the core. Now in this case, we didn't have to explicitly apply that to obtain the value of b, because of the simplified form of this expansion. We saw that as y goes to infinity, the only way you can keep the solution bounded is to have b going to 0. But there are other problems where you may not have such unbounded natures arising, in which case you have to explicitly enforce matching to obtain the coefficients. Whereas here it happened automatically. So if we had started by saying, look, I want this expression, right, to match that of the core solution as y goes to infinity, you would see that regardless of the value of c, as y goes to infinity, this term, because of the exponential minus y, will go to 0. This term would start going to infinity, but you remove it off by setting b equal to 0. So the only thing that survives asymptotically as y goes to infinity is minus I, and that exactly matches the solution in the core. So we have satisfied the condition of asymptotic matching. This is something that arises in a standard fashion in singular solutions. So maybe in other examples that we do, we will be required to recognize this in a more explicit fashion. Here it kind of automatically matches the core solution. Okay, so let us now write out the full solution after having discussed that point. So let us first start with, as we did before, with the leading order. So the leading order part of this is just yet another thing. So because it's matching now, the uniform solution, of course, for the entire problem has to be obtained in a piecewise way. So we say that if R is in the core region, right, then I should retain only minus I, whereas if I'm near the wall region, I should switch over to H naught. But because the matching has been satisfied, I can just use a single expression, which is this expression for H naught bar, because automatically if y is close to the wall, right, where basically this solution, if y is close to the wall, this exponential term becomes 1 and the boundary layer solution starts to dominate over this core part of the solution. But if y starts moving further away from the wall, right, it starts approaching infinity, which it will, because remember y is just the r coordinate times rw to the half. So for large rw to the half values, for large frequencies, this y will really take large values as I start approaching the core. And when that happens, this term will go to 0 and only minus I will dominate. So this is the benefit of asymptotic matching. It gives us a boundary layer solution which is uniformly valid both in the near boundary as well as in the core, right? But to obtain this solution, I have to first solve the core problem, which I did before doing the boundary layer scaling, because that is what provides me the condition via asymptotic matching to calculate the coefficient B, right, which we found here to be 0 as the only way to match with the core region. Okay, so now this is actually not just the solution near the boundary layer, it is the solution valid throughout the domain after we did asymptotic matching. Okay, so now I can write that U is imaginary part of e to the power I RWT, H naught bar by RW. And so if I now extract out the imaginary part, starting with the constant contribution. So I'll have a 1 by RW factor coming out. Because this first term is minus I, I'll take the cosine term from here. Right, and I just get minus 1 coming from this term. In the same way, I'll take out the imaginary part coming from yes, so minus I times cos is the imaginary part from here. So I get plus cosine minus y by root 2 yeah, so that is basically cosine y by root 2. The minus sign doesn't make a difference, times the exponential of minus y by root 2, which is the exponential decay away from the wall, plus now again the 1 by RW factor, this time the sinusoidal part from e to the power I r omega t, multiplying the real contributions from H naught bar, which is just root 2, and the minus sign cancels off with this minus sign, so I get sine of y by root 2. So this is the full asymptotic solution for U, right, in the limit of RW being very large, right, noting of course that where the coordinate y, now remember what is y? Let's go up here. Yes. So y is RW to the half minus R, correct? Yes, y is RW to the half minus R bar, but R bar is itself RW to the half R. So y is basically RW to the half, remember minus R bar, but R bar is RW to the half times R, so it's 1 minus R, where R is the original coordinate that goes from 0 to 1. Okay, so now here you can see the full structure of our boundary layer solution revealed quite beautifully. So if you are in the core region, right, if R is essentially close to 0, right, then y takes on very large values, provided of course RW is large, right? So in the large frequency, RW is a large number. So when R is close to 0, y becomes a large number. If y is a large number, then these exponential terms will basically knock off these boundary layer parts of the solution, right? And all I'll have is a out of phase plug response, which is the response in the core. This is what we had derived immediately when we looked at the original problem in the limit of large RW and simply set RW to 0. We got only the core solution, right? And the problem then was we knew we could not understand the solution near the wall. But we now have done that using boundary layer analysis or singular perturbation methods. And what we now see is if R is close to the wall, so that 1 minus R is sufficiently small, it negates the effect of this RW to the half, so that Y becomes an order 1 quantity, in which case these exponential terms and the cosine factors become important, and it modulates the core solution such that in the limit of R exactly going to 1, Y will go to 0, right? And you will see that you will satisfy the no slip boundary condition, because this term basically becomes 0 when Y is 0. This term becomes 1 when Y is 0, and minus 1 plus 1 goes to 0. So I'm able to recover the no slip condition when Y tends to 0, as well as the core plug flow when Y tends to infinity or R goes to 0 from this complete singular perturbation solution to the problem. Alright, so now let us do what we had done in the case of the small frequency limit. Let's go to Mathematica and let's look at what the form of the solution is if I plot it. So you see here I have now given a value for inverse RW is basically 1 by RW. I've taken a value of RW that's reasonably large, about 40. So 1 by RW is 1 by 40. I then wrote out the solution for the fast frequency as exactly as we obtained. And U0 is only the plug solution obtained in the core region if I had not done the boundary layer singular perturbation analysis. And I now plot the two of them here. So the blue line is the actual singular perturbation solution, right, after boundary layer analysis. So it goes to 0 near the walls, the velocity. Whereas this red dashed line is only the core solution, the plug solution. And remember, this core solution is out of phase with the flow, whereas you get some in phase contributions when it's near the walls. So let's play that. So you see now that it's only close to the core region that you really attain the kind of flattened plug flow solution. But as you approach the walls, you have modulations to account for the fact that the drag on the walls becomes important and the viscous terms start to modulate and have an effect on the plug flow. Indeed, you see that it's only in a rather small region that the core solution is actually valid. But that does not mean that you can say the core region is unimportant, because it is the core region solution that was actually crucial via asymptotic matching to allow us to obtain the boundary layer solution. Right? In fact, it is what showed us that we had a boundary layer problem in the first place, and then when we were solving that boundary layer problem, we could not have we could obtain one coefficient, one unknown constant from the wall, but we needed the core solution to obtain the other constant via asymptotic matching. And you can see nicely now that really in this case the problem is nothing like parabolic. It's like some sort of plug flow with modulations near the wall, and it has a much more complex response behavior. And this is something closer to what one would expect in the heart, especially in the large arteries, right? So in the nice thing about the cardiovascular system as a fluid mechanics problem is that it scales the entire range of this RW. So if you're in your very small arteries, so let's say basically we have omega in the units of seconds to be order 1, right? Because we beat roughly once, our beat frequency is of order 1 hertz, right? So given that omega is fixed to that value, RW really depends upon the radius of the pipe and the viscosity of the blood. So for fixed viscosity, it really depends on the radius of the channel. And we have a whole hierarchy of dimensions in our body. So in the large blood vessels, like the aorta, close to our heart, we will have a large radius, and in that this high frequency limit is more relevant. So the flow profile is going to look something like this, a plug flow but with modulations near the wall. Whereas if you go down to the smallest arteries and veins in a body which have micro scale dimensions, there we might expect the flow to be closer to the small frequency limit. Of course, now there are many other complications. The fact that the blood is not a Newtonian fluid and has corpuscles and blood vessels and so on have introduced many non-Newtonian effects. But here from this analysis you can see what role the pulsatile flow has to play in the nature of the solution. And all of this we have been able to do analytically without doing a single computation, and in fact the analytical solution is going to be extremely valuable if you do want to do a numerical simulation, because you now know what to expect beforehand and you have approximate solutions with which to verify any numerical simulation. So this should now give you a feel for what our singular perturbation methods have allowed us to do. Right? We could, when we obtained the problem first, we saw in the high frequency limit that we got only a plug flow. Now we understand that that's only valid in the core, as we could see immediately because we didn't satisfy the boundary conditions. And then the singular perturbation method calls for a rescaling near the boundary conditions that are not satisfied, so that we can retain the highest order derivatives in the problem, mathematically speaking. That rescaling then allows us to solve another perturbation problem near the wall. And that problem incorporates the wall boundary condition, and we also have another boundary condition from asymptotic matching, matching of the near wall solution to the solution away from the wall, and that gives us a complete solution that is uniformly valid throughout the domain after matching the core solution and the wall solution. And this is the form of the uniform solution that we obtained, that I have plotted here. So you see now that the perturbation method can handle both types of problems, both regular and singular. That is, it can handle problems where the small parameter doesn't change the fundamental mathematical nature of the problem, but it can also handle problems where the small parameter multiplies, let's say, the higher order derivative, like a viscous term. But you do have to do some rescaling and some extra work. This, of course, is you can now think back to the algebraic equation we solved, where you had a quadratic where the small parameter epsilon multiplied this x square, the second order term, and which therefore in the limit gave us only one solution, and we had to rescale that problem in order to capture the other solution. In the same way here, because we lose the viscous terms, we need to rescale the problem in order to capture the effect of the walls. Now in this example, we have been able in each case to solve the perturbation problem analytically and thereby obtain an approximate solution. So by that I mean, take for example the case of the limit of high frequency. Yes, so where we obtain this boundary layer solution. After scaling the problem correctly for the boundary layer and making a change in coordinate here, equation 10, we finally obtain this equation here in terms of the coordinate y. So this is the boundary layer equation. We then make a perturbation expansion for this boundary layer problem, and we find that at leading order that we obtain the equation for h naught bar. Now at this stage it turns out that in this case the problem is simple enough that it's amenable to an analytical solution. But you could ask, suppose we land up with a differential equation here for this h bar naught, which is something we cannot solve analytically. What then is the use of all the hard work we put in to derive this approximate perturbation problem for the boundary layer and for the entire problem? So it turns out that even if you could not solve this problem analytically, of course you could solve it numerically and then somehow try to match this to the core. So what I mean is you could solve this problem numerically in the coordinate y and then take a large domain in y and then put a boundary condition such that as y, so that at one wall you have no slip and at the other end of your y domain you let the solution fall off to 0, and then you would get kind of a numerical solution to the boundary layer problem. But even if you could not do that, the exercise that we have gone through to reach this point is still extremely useful. So one way to see this is that this whole boundary layer exercise will allow us to predict how an overall macroscopic observable depends on the parameters of the problem without even solving any numerics. So for example, imagine you wanted to calculate the shear stress at the wall or the shear stress exerted by the flow on the wall in the case where the frequency is large. So one way to do this, of course, is to solve the problem. If we could solve the problem as we have done here analytically, then we calculate the velocity field in the boundary layer and we can compute the shear stress that way. But even if you cannot solve this problem, we can still determine through our analysis how the shear stress will scale with the frequency, that is in this case with the Strohal number or 1 over Rw. And that already gives us a lot of information about the problem, even in the case where we cannot solve the differential equation for H0 bar. So to see this in action, right, let's say we are interested in so we wish to calculate the shear stress at the wall. By the way, for cardiovascular problems, the shear stress at the wall is an important parameter that one would like to compute because it is related to issues like which are responsible for the formation of blood clots. And so it's an important thing that one would like to measure, or even compute through numerics or through fluid mechanical calculation. So yes, let's say we wish to determine this. So the shear stress at the wall in our problem is simply, I'm writing now in terms of the native dimensional variables. So it's the shear stress acting on the R surface at the wall, right, in the Z direction. And this is simply mu times du star by dr star. Again in the notations of, the original variables in the problem. So now we can replace this by its non-dimensional framework. So we get u times you will have here du by dr, the non-dimensional variables. And what pops out, of course, is uc, which is gr square over mu. And the r characteristic scale is, of course, the radius of the pipe. Right now we are in the original non-dimensional variables. And the mu's cancel. So what this gives us is basically tau rz non-dimensional is simply equal to du by dr. Right, this is what we could have written down directly, of course at r equal to 1, I'm sorry. This has to be calculated at r star equal to capital R at the wall, which is equivalent to r equal to 1, right? So we could have written this down directly if we simply recognize this appropriate scale for tau rz is g times r, right? Because this is the pressure gradient and g times r is has the units of pressure, which is the same as the units of shear stress. Alright, so this is an expression in terms of our original non-dimensional variables. Now in the limit of high frequency, basically for either limit, we wrote u in terms of its companion problem u hat, right? And in turn we wrote u hat in terms of h. So I can now write it as follows, that approximately I can write tau rz instead of u, I can write it in terms of the imaginary part of u hat, and from there I want to write it in terms of dh, pulling out the time periodic part. So that's equivalent to saying I want to calculate the amplitude of the shear stress, because I know the shear stress is going to oscillate, and the oscillatory behavior's time period I already know as 1 over omega or 2 pi over omega. So what I really want is the amplitude. And so that amplitude which I'm interested in, tau rz, the amplitude, right, would scale as dh by dr at r equal to 1. But now in the high frequency limit, remember, I replace h in terms of h bar upon rw. That was because I rescaled the velocity in terms of you're using the velocity scale coming from a balance between pressure gradient and inertia. So this term can be written as dH bar 1 over Rw times dr. But then this in turn, I now, if I want to write this in a form that I can use to compute the stress from the boundary layer equation, or the equation for H bar naught, remember that I had transformed the R coordinate to R bar and eventually to Y. And so the relationship between the two has a 1 over Rw to the half factor right here. So R is R bar divided by Rw to the half, or equivalently R is 1 minus Y divided by Rw to the half. Yeah, right, what we have here. So this means this is equal to, so I can write it as dH bar by dy. I'll get a negative sign because of the relationship. And then I get Rw to the half as well from the boundary layer scaling. And then I have the original R by W. Right, so this half, this basically becomes half as I cancel this out. And finally I can write this again ignoring the negative sign. I just want the magnitude. So I Rw to the half, and H bar, remember I can treat it in terms of its leading order term. So H bar was H bar naught plus higher order contributions. If I just take the first term, this then becomes by dy. So what we get from all of this is that the non-dimensional shear stress at the wall, the amplitude, right? So I'm interested only in the amplitude here. Basically goes as is basically given by approximately by 1 by Rw to the half d by dH naught bar dy. So, all right. So now I could get a good estimate for this if all I have to do is calculate H bar naught and take its derivative with respect to y at the wall. So at y equal to 0. Yes, I should have written that there. So r equal to 1 is of course y equal to 0. Right. So in our case now we were able to solve dH naught bar. We were able to solve this equation for H naught bar. Therefore we have the solution that we can simply differentiate right here, this solution, which is an order 1 quantity. You see it has no dependency on Rw anymore as expected, because we have by construction basically the way we constructed the problem for H bar naught. So it is just something which has roughly the magnitude of some number between 1 to 10, right, based on our scaling. So if we have solved the solution, we simply differentiate this expression and evaluate it at y equal to 0 to get the exact answer we're looking for as the approximate amplitude of the shear stress. But this is where the point I was trying to make becomes very clear. So even if you could not solve this problem for H bar naught, all that means is you can't determine this numerical factor. But from our entire scaling analysis, we know that H bar naught will not depend on Rw at all. And in fact, we also know that its magnitude must be order 1. So therefore, I can write this as 1 by Rw to the half times some constant C, right, where C is a order 1 numerical factor. So you see that even without solving the problem, setting up the whole asymptotic calculation has allowed us to predict how the wall shear stress will vary with the non-dimensional frequency in the limit of it being a large frequency. Similarly, you could go back and see how it would scale if the frequency is small by looking at the solution we obtained, or the perturbation problem we obtained in the other limit. Again, we were able to solve it in that limit of small frequency, and so one could calculate this exactly. But even if you can't, you can still derive the scaling. In that case, you will see tau, the non-dimensional tau Z will just go as some numerical factor. And because it basically behaves quasi-statically and the dependency on the frequency is not strong. But here you see this, the appropriate dependence coming out cleanly. And this C, as I said, is just an order 1 factor. So what the usefulness of this relationship is that I just have to determine this factor, which I can do in principle by just 1 or 2 experimental measurements. Right? So you take such a pipe, you run an experiment, and you kind of look at a few values and fit it, and you just have to determine C, which will be a straightforward calculation. I mean, a straightforward fitting to the data. And this is something that you could do for a much more complex problem. So in this case, our problem for H bar naught was solvable because we looked at flow in a simple circular pipe and took a simple fluid, so on. But if your problem is more complex, you have a more complex constitutive equation for the fluid, you have a more complex boundary geometry for the wall, you may not be able to solve it analytically. But you don't have to go all the way to numerics immediately. Instead, by doing the asymptotics, you can find out how the main overall quantity of interest, right, scales with the parameters in the problem. You can get a scaling relationship like this, as we have derived here. And then all that remains is to find the numeric constants, which you can do by just doing one numerical simulation, let's say, for a given value of the frequency and the properties of the fluid. And this sort of scaling remains true even if I change the geometry of the problem, as you can convince yourself by thinking through the steps that we adopted, and none of them would really change other than the fact that the let's say length scale inside R omega won't be the radius of the pipe, but some other appropriate length scale for the channel. And so you can see it really retains utility and still remains a powerful method, even for those cases where we may not be able to solve the final problem for the perturbed solution analytically. Okay, so that brings us to the end of this interesting example of pulsatile flow, where we've been able to entirely analytically obtain a solution for both limits of the problem, and thereby understand, get quite a bit of physical understanding, I think, of the problem, and how if one varies the frequency, you can get very different solutions, from going from a near parabolic like modulated solution in the low frequency limit to a near plug flow solution in the high frequency limit. So with that, I thank you and look forward to talking to you in the next lecture, where we will look at one more interesting example of the application of perturbation methods. Thank you.